In this session, let us focus on a question from CSIR Net December 2024. Here we are given canonical transformation relations. We have to identify the generating function. So in these types of problems where we are given canonical transformation relations and we have to find this generating function, what we do is first we determine the type of generating function. Among the given options, all of them are the functions of small p and capital Q. Function of small p and capital Q. So this is type 3 generating function. There are 4 types of generating function. F1 is a function of small q and capital Q. F2, type 2 generating function, it is a function of small q and capital P. Type 3 is function of small p and capital Q, and type 4 is function of small p and capital P. Now in this case we have type 3 generating function because in all the given options we have functions of capital Q and small p. Now we have determined the type of generating function. Once you determine the type of generating function, the second step is to write the differential relations. So there are some relations, differential relations for every type of generating function. For type 3, how we write the generating function, let's see. What are the variables used in generating function type 3? P and Q. These are the variables used, P and Q. So we partially differentiate F3 with respect to P and Q. Del F3 upon del capital Q. Now in the LHS we write the canonically conjugate variable to denominator. So here in the denominator we have small p, canonically conjugate variable to small p is small q. Here we have canonically conjugate variable to capital Q is capital P. Now about sign. If derivative is with respect to small p or capital Q, then it will be negative. Here we have derivative with respect to small p, we will put a negative sign. Here also we have derivative with respect to capital Q, we will put a negative sign. So this is how you obtain differential relations. I hope you understood how you find the differential relations. I will give you one more example to give you more clarity. Let us say the generating function is type 1 generating function. In that case the variables used are capital Q and small q. So you will write the partial derivatives with respect to the variables del F3 upon del Q, del F3 upon del capital Q. Now in the LHS you will write canonically conjugate variable to small q, which is P, and canonically conjugate variable to capital Q is capital P. Now derivative with respect to small p and capital Q are negative. Here derivative with respect to small q, it is not negative, there will be positive sign. Here derivative is with respect to capital Q, therefore you will put a negative sign. So these are the differential relations for type 1 generating function. Now let us come back to our problem. In the step 1 we determined the type of generating function. In the step 2 we wrote the differential relations. We got the relations to be Q is equal to minus del F3 upon del P and capital P is equal to minus del F3 upon del capital Q. Now in the step 3 what you will do is you will express the LHS of differential relations in terms of variables used in the generating function. So what are the variables used in generating function? It is P and capital Q. So we will write the LHS, which is Q and capital P. We will express them in terms of small p and capital Q. For this we can use the canonical transformation relations given in the question. So we have to write Q as a function of small p and capital Q, and in the second differential relation, this is second differential relation, in the second differential relations we will write the LHS P as a function of small p and capital Q. First transformation relation is given to be capital Q is equal to ln of 1 plus q raised to 1 by 2 cos p. Let us write it here. Capital Q is equal to 1 plus q raised to 1 by 2 ln of 1 plus q raised to 1 by 2 cos p. From here we have to solve for q in terms of p and q. If we take exponential in both sides, we will get e raised to q is equal to 1 plus q raised to 1 by 2 cos p. From here we can write q raised to 1 by 2 is equal to e raised to q minus 1 divided by cos p. This implies q is equal to e raised to q minus 1 divided by e raised to q minus 1 the whole square divided by cos square p, which is q is equal to e raised to q minus 1 the whole square sec square p. So now we have written small q as a function of small p and capital Q. Now let us express capital P as a function of small p and capital Q using the second relation. So we are given capital P is equal to two q raised to 1 by 2 times 1 plus q raised to 1 by 2 cos p times sin p. Now we have found that q raised to 1 by 2 is nothing but e raised to q minus 1 divided by cos p 2 times e raised to q minus 1 divided by cos p times 1 plus again q raised to 1 by 2 is e raised to q minus 1 divided by cos p times sin p. Cos p gets cancelled. We have sin p divided by cos p is tan p. So we have 2 times e raised to q minus 1 tan p times 1 and minus 1 gets cancelled, e raised to q. This is capital P. Now we have expressed small q and capital P. Let us put this in differential relations. In the differential relation 1, if we put q is equal to minus del f3 upon del small p, this is differential relation 1. If you put q, which we found here, this one, in the LHS we will get e raised to q minus 1 the whole square sec square p. This is equal to minus del f3 upon del p. Now in this step what you will do is you will integrate for finding f3. You will do partial integration. So we have e raised to q minus 1 the whole square sec square p del p integrate. This is equal to minus integral del f3. From here we will get f3 is equal to e raised to q minus 1 the whole square. There is a minus sign outside, tan p plus some function of capital Q, because we have to consider this when we are doing partial integration with respect to small p, and there can be some constant. At this point itself you can reach to the correct answer. The correct answer will be option 4, because only option 4 contains minus of e raised to q minus 1 the whole square tan p. But let us find what this c of q is, if there is a function of capital Q is there or not. For that, what we use is, we will put this f3 that we obtained in the second differential relation. Second differential relation is capital P is equal to minus del f3 upon del capital Q. P is equal to minus del f3 upon del capital Q. Now P, we obtained P to be equal to 2 e raised to q minus 1 tan p e raised to q. Let us put it in the LHS. 2 e raised to q minus 1 tan p e raised to q. This is equal to minus del by del q of f3, we just calculated it. It is this, minus of e raised to q minus 1 the whole square tan p plus c of q, some function of q, plus some constant. Now let us do the differentiation in the right hand side. Then we will get e raised to 2 e raised to q minus 1 times e raised to q tan p minus c dash of q, and derivative of constant is 0. In the LHS we have 2 e raised to q minus 1 tan p e raised to q. Now for both LHS and RHS to be equal, we need c dash of q to be equal to 0. This means c of q is equal to constant. Now c of q can be any constant, it can be 0 also. So if it is 0, then the generating function is option 4. I hope you understood this explanation. If you have any doubts, please comment. Thank you for watching the video.